Welcome back to the ChemDoctor, and this is the second video on the playlist that deals with Le Chatelier's principle, and it is part of the playlist that deals with chemical equilibrium. All right, and in this video what we're going to do is look at what happens to a chemical reaction at equilibrium when we alter the pressure of one or more of the components of the reaction. So let's see, for the reaction that we're going to look at, it'll be carbon monoxide plus hydrogen gas. And our model system here is going to involve components that are all in the gas phase. The thing to remember about this that's important is that you need at least one entity or species that's in the reaction to be in the gas phase. So if we were dealing with a heterogeneous equilibrium where one or more of the components was a solid, then the argument that we're making here would not apply to those particular components and only apply to the component that is in the gas phase. Now, let's say that we have an equilibrium concentration of each of the species that are in here. And for the carbon monoxide, we're at 0.105 molar. For the hydrogen, we're at 0.114 molar. And for the methanol, the CH3OH, we're at 0.185 molar concentration. We're in a 1 liter flask. We're at equilibrium, so the temperature is fixed. So fixed temperature, and the Kc for this reaction is normally 136. This is a large equilibrium constant. Okay, and that means at equilibrium that we have a preponderance or a high concentration of products by contrast to the reactants. If I was to draw a seesaw representation for this, like in a playground, the seesaw would be leaning to the right and down. So our products would be on the part of the seesaw that's pointed down, and our reactants would be pointed up. Just another way to think about this. All right, now, in Le Chatelier's principle, what we're saying is, okay, we've got this reaction, it's at equilibrium. These are the equilibrium concentrations of the reaction, and they're all in the gas phase. So let's say that we reduce the volume of the reaction vessel. So we're going to reduce the volume of the reaction vessel. Now, before we get into the nitty-gritty of this, remember, since we're dealing with all gases here, well, and for whatever kind of reaction we have, if there's a gas phase component in it, then it obeys the general gas laws. All right, so we have to remember about Boyle's law here. And what Boyle's law says is that if the volume is increased for a gas, then the pressure has to go down. Because what Boyle's law says is that the volume of a gas, of an ideal gas, is inversely related to the pressure. So similarly, if the volume is decreased for an ideal gas, then the pressure has to go up. So we're going to be decreasing the volume of this reaction. All right, now, the first thing I'm going to do is convert everything that we have here in order to take you through an example that shows you what's going to happen here. We want to convert all these concentrations into moles. Remember how that's done when you're dealing with a molarity. So I'm just going to show you one of these down here on the right. So if we have 0.105 moles of CO per liter, because we are in 1 liter, all right? And we multiply this times the volume. The liters cancels, and we're now in units of moles. We're in now in units of moles. All right. So we can convert each of these numbers into moles because we're in 1 liter for our reaction vessel. So I'm just going to go through and change the unit here. Okay, now what I said to set this problem up. So what we're doing is we're going to change the pressure of the components that are in this reaction, and the way that we're doing it is by manipulating volume. So in Le Chatelier's principle, when I talk about changing pressure, it's changing pressure by virtue of the fact that we're going to change the volume of the reaction mixture. All right, and what we're going to do is reduce the volume to 0.5 liters. So I'm going to go through and we're going to divide each of these mole values by a half a liter, right? Because we've reduced the volume by 0.25. Now, let's go ahead and recalculate our molarity. All right, so the molarity now for the carbon monoxide is going to be 0.21 molar. Notice that the molarity went up. It should have went up because we decreased the volume by literally 1/2, right? We cut this volume in half. So we've compressed all of the gases that are in this reaction. All right, and for the hydrogen, we're now going to be at 0.228 molar. And for the methanol gas, we're going to be at 0.37 molar. So now, to keep us straight here, these are all non-equilibrium concentrations. These are now initial concentrations. We reduced the volume of our reaction mixture, which caused a change in pressure. So these are now initial concentrations. Initial concentrations, they're non-equilibrium. So our reaction needs to respond to this because it wants to go back to equilibrium. So let's figure out what happened to the relationship between the reactants and the products. And the way we're going to do that is by calculating Q. So remember when we calculate Q that Q has exactly the same form as K, except that we plug in non-equilibrium concentrations. So my Q is going to be 0.37 divided by 0.21 and divided by 0.228. However, the hydrogen has a coefficient of 2, so it'll be 0.228 quantities squared. So my Q value for this reaction is going to be equal to 33.89. 33.89. Now, notice that the equilibrium constant is 136. So the Q value in this case, Q is less than K because the Q value is about 34, which is, you know, easily less than 136. So Q is less than K. And what that means is that the reaction must shift to the right to get back to equilibrium. Okay? Now, you can think of it this way, that what ended up happening when we look at our little seesaw here is that when we reduced the volume of our reaction, which caused the concentrations of all the species in it to be increased, that the seesaw actually was shoved down this way. And in order for us to get back to the point where the products are at a much higher concentration, or at least at the correct concentration relative to this relationship between products and reactants, where Kc is 136, we had to convert some of the reactants back into products. All right, now there's another interpretation here that I want to add to this. So we reduce the volume of the reaction, that had the effect of increasing the pressure of each of the components in here because we increased concentration. The reaction had to shift to the right. Now, if you look at the balanced equation, you can see that on the left side of the equation we have a total of 3 particles of gas, and on the right side we have 1 particle. So coming back to Le Chatelier's principle, all right, we reduced the volume of this reaction, which had the effect of increasing pressure. The reaction, in order to get back to equilibrium, wants to shift away from this increase in pressure. And the way that the reaction did it was by shifting in the direction that produced smaller numbers of gas particles. Smaller numbers of gas particles. So in a Le Chatelier problem, when you have an increase in pressure due to a decrease in volume, the reaction will always shift in the direction that produces smaller numbers of gas particles. Now, if you have trouble rationalizing that, you can approach the problem the way I showed you how to do it here, where you figure out, okay, what's the concentration change going to be because of the reduction in the volume? Calculate your Q value, all right? Compare Q to K, and then you can determine which way the reaction is going to shift to get back to equilibrium. And with that, I'm going to go ahead and close this video.